two things. First off, we are going to get to functors, but first we're going to start with this thing called higher kind of types. What I'm trying to do with this is to give you a sense, a taste of like what some of this like more seemingly complex functional programming stuff is about. So higher kind of types are sort of a way that you may not be used to thinking about the structure of things. So if we think of things that have very defined discrete structure, ints, strings, bools, we know a lot about these, right? We know the exact set of operations that we can do with these, that kind of thing, right? A list, well, we know about the list part of the structure, but we really have no, I mean, by definition, this is parametrically polymorphic. We have no idea what T is. We can say nothing about it, right? And then IEnumerable is almost kind of like a weaker form of list, right? We know a little bit less about it. Like you could have an IEnumerable that's actually a list, sure, certainly. This is C# for people who aren't familiar with that. You could have an IEnumerable that's a linked list. You could have an IEnumerable that's a tree. You could have an IEnumerable that's a queue or a stack. So all we really know is that IEnumerable has some structure, the ability to step through every element in it in some order. It's not guaranteed to be consistent or stable. And we know nothing about the T. Right? So we're kind of going from like, we know a lot about this, we know a lot about some of this and nothing about the rest, to we know kind of something about this and nothing about the rest. Okay. So if we were to kind of look at that as the parts that are concrete and the parts that are abstract, ints are concrete, lists are concrete, but T, that's totally abstract. And I'm just showing you some different syntax here. Here's the C# syntax. That's kind of the Elm, PureScript, Haskell type syntax. Reason, if you're looking at that language out of Facebook, they use that kind of syntax too. Okay, so for our purposes, I kind of had this in green. It's like partially abstract. Let's just think of that as fully abstract for our purposes, fully concrete, just with a very small set of things it can do. All we can do is like iterate, like use it in a for loop. So what I want to do is I want to say, like, well, what's the next step of abstraction then? If these two are kind of the same, this isn't really like a step up in abstraction. What would the next step be? Right? The T is fully abstract, but this is fully concrete. So the next step is to make this also abstract. Right? So now we have an F that we know nothing about, parameterized by a T that we know nothing about, which is pretty abstract. We know very little about that structure, other than it's parameterized by one type. Right? That's all we know. And there's no syntax to write that in like this kind of syntax. Okay, so what we do is we talk about F as structure. F is some kind of structure. We know nothing about it. It's parameterized by type T. But we could already come up with examples of things that fit this structure. So what is some type that's parameterized by another type? Like any type that we can think of that has one like type parameter, like one open thing in its angle brackets, T. Say again? Map. Well, map has two parameters. Oh, right. Yeah. But list would work. Queues and stacks would also have one type parameter. A maybe would have one type parameter, right? So there's a couple things. Yeah, lists, queues, maybes. Promises have a type parameter. The return value that they give back.
Is there a name for like just a wrapper? All it does is give back. I don't know if there's a name for that type of thing.
Like maybe?
Except there's no nothing. Like identity? Like an identity.
Yeah, I guess that would be identity.
Wrapper.
Mm-hmm. And it only holds the value but has no additional interesting structure. So that would be like a trivial kind of wrapper. So like identity is usually, there's like an identity type for that. So channels, we talked about like streams and promises. Channels can also, because the channel's producing a value of some type. What about a Redux store? You say my Redux store is parameterized by this type, the state that's inside it, right? You might not think of Redux store as a thing that's parameterized by another thing, but certainly if you were to write a flow type for that, we would see that. Okay, so what can't fulfill this structure? What doesn't fit this? You mentioned one. Map. Because that would have to be an F of T, T2, or F of AB, or something like that, right? And again, the choice of these is completely arbitrary. These can be anything you want. Traditionally, this is either F or M, and these are ABC. Just that historically, that's just sort of idiomatic. But if we're looking at more like the C# style, that's why I kept it as T. So yeah, map cannot fulfill this. Any type that requires 2 inputs in the angle brackets, or 3 or 4, or 0. Exactly. String cannot fit this. That's a good point. A tuple needs 2 type parameters, right? The type of the first element, the type of the second element. So that can't fit this. Right. Redux reducer can't because it needs both the type of the message and the type of the state. Okay, so what we're doing is we're thinking in terms of, we're talking about like the f of t or f of a, we're thinking in terms of just, it has some structure, we don't know what that structure is, and we're kind of we're letting go of the particulars of any particular structure. And the same way that we can put constraints on things, so here's a C# function parameterized by t, where t is an I something, right? So we can use any type in there as long as it's an I something. And we do the same thing here. This is that exact same thing written with different syntax. This is like a kind of Haskell pure script, except I'm using a single colon. So I something, which is a t. That's the constraint on t right there. And then we say it takes a list of t and gives you back a t. So it's the same thing. It takes a list of t and gives you back a t, where t is an I something, where t is an I something. But there's no reason that you can't have multiple constraints on each of the things, right? So both the f and the t can each have their own constraint. And you can have multiple constraints on either one of them. So we can say f has to be a something else, and t has to be a something. And you can write a function in terms of that signature, where as long as those things hold, it's valid and it will compile. So you can put constraints on both. And if you had, it doesn't just have to be f of t. It can be f of a and b, right? Like an either type or a Redux reducer type. And you can have constraints on any of those. Okay, so that is higher kind of types. We're just, the idea that we can be generic in our structure is a concept. That's the higher kind of type concept. And we'll get back to where that's useful in a minute. Okay, so now on to functors. So we have the structure, parameterized by some type, and what we want to talk about now is a particular structure. The functor is the structure that we're interested in. Like what a functor is having this particular structure. So we have, f of a can be many things. The thing that makes one f different from another is that it has a different structure. And by structure, it's like rules about how you use it. Okay, so a functor has one specific thing that it can do. Not all structures are like this, but in functor's case, there's like this one thing that it can do. Often these structures have, at most, like 2 things they could do. That would be considered a pretty like big structure, like a maybe too complex, needs to be broken up into multiple. Generally, they just do one thing. And the structure that we're interested in with functor is the skill we have is the ability to do something to the value inside that structure without knowledge of the structure itself. So we have here the functor is the list. So list is a functor, generally. And the value inside it is of type int. So we have a list with some int or ints inside. And the skill of the functor is we can do operations inside it. I think everyone here has done this with map, right? But think about it as this is an example of a structural thing that can happen. And so if we can apply some function, like an int to string, to the functor takes care of then applying the function. We apply the function to the functor, which applies it to the value inside, and it gives us back a new one, right? I think everyone here's played with map as an example of that. And of course, the type doesn't have to change. It is allowed to change, but it doesn't have to change. So if we do something that's int to int, we end up with an int. Okay? And that gives us, so the list, the functor itself, part of its role in this is that it allows the outside world to hand it arbitrary functions as long as the types line up, and it doesn't know what they're doing. So there's 2 parts of this. the skill of the functor is that I outside can hand it a function, and I don't know what it's doing inside. Like, there's all kinds of different functors. I don't know how it manages to apply the function to the value inside. It just does it. It figures that out. And I get back a new value. From the functor side, it says, I'm going to be handed functions I know nothing about. I don't know what they do. I just apply them to the value inside and follow the rules that makes up what kind of structure I have, and I hand them back the new value. So we have two sides that are sort of intentionally not knowing a lot about what the other side is doing. And that's a good thing, because it keeps them very separate. So the list just knows, hey, you have a thing. I know it's A to B. Great. I have an A. Therefore, I can give you back a B. I know how to do that. And of course, this is invalid. This will get rejected by your type system. If you have a B to C, you can't do that because it's a list of A. That doesn't line up. That make sense? Hopefully, yeah. So we've seen, probably everyone here has seen something like list.map. And here's the C# type signature for reference. But it's a function from A to B and a list of A, and you get back a list of B. Okay. And that's what it would look like in C#. Okay, so that's good for lists. We can map over lists. Great. But it would be nice if we didn't actually care kind of like the specifics, because this map operation is much more general than just lists. Right? Lists are an example of something that can be a functor, but they're not everything that can be a functor. So really, we just want to know that if we have an A to B and an F of A, then we can get to an F of B, right? Where F is a functor. So as long as it matches the type, we're good. So we put that constraint on F. So by saying F is a functor, it means it knows what to do with map. It knows how to handle, it's got this map operation for whatever structure it has. And as long as, and all map functions will then have this signature. Okay, so we've got all these things, promise and lists and channels and whatever. How many of these can be functors? Remembering that to be a functor, you have to be able to implement this for your type, whatever your type is. So if you can write a function where replace F with your type and it works, then you're a functor. So can we do this with like a maybe? If you have like a maybe, can we say map over that maybe with the maybe of int, and you map over it with to string, and we get back a maybe of string? That seem reasonable? Okay. A promise, can we map over a promise? That's actually what then is sort of doing. Then is a little bit different, but it's along the same vein as taking the previous value and producing a new value. Then's a little different in that it doesn't guarantee you're going to get a promise out. Like, it can change into something else. But that's sort of, if you use it sort of idiomatically, you'll probably get another promise back. So that's kind of like mapping over a promise. Can we map over a Redux store? So, actually, let me see. Okay, yeah, so let's go through. Okay, so list, we know we can do list, right? Because we can put list of A, it's valid to take a function from A to B, take a list of A, and get back a list of B. That works. We can do that with the maybe. Makes sense. We can take a maybe of string and get back a maybe of int. That seems reasonable, right? Now, the map, that should just be map, not map list. The map function here, it's logic, because every functor gets to decide what it means to map over that structure. In this case, we apply this function to every single thing in that list to get back the new list. That's what map means in the context of list. In the context of maybe, what does map mean? It's pretty different, right? There's potentially a single value, and maybe not even that, maybe no values. So map, in the context of maybe, says, well, if I have a value, great. Apply the function to the value inside there and give me back a new just value. If I don't have anything, then nothing to do. Just give back the nothing. So it's the same function, the same signature from the outside perspective. It's just A to B and F of A give you back an F of B. But the internals, they're doing very different things. Okay, so that works. Promises, same sort of thing, except that in the context of this, if we were mapping over a promise, it wouldn't be quite like .then. It would be more like give you back a new promise that has that function auto-run on the result as it comes out, right? It's kind of like as the value is coming out, we run it through this map function and then return the value. And if the promise rejects, of course, that's like the nothing case of the maybe, and we just do nothing. Or we get back whatever like error case that was. Okay, so the Redux store, we could have our Redux store, so here's our function. We could have our reducer, and normally it comes in this way, but we could flip it around to look like that. And then we would have our nice A to B right here, right? Except this isn't A to B. This is A to A, right? So if we accept this signature, it means that the reducer can take in a store parameter of some type and give you back a store of some other type. That the reducer would be allowed to change the structure of its state. I don't think we want to let that happen. I think we explicitly do not want that to happen. I think it is very much that we want to say, we're going to give you a message and the old value, and you're going to give me back the exact same type with potentially modified values, right? So store cannot be a functor, because even though it has the one type parameter, so it's an f of a, it fulfills that, it cannot be an A to B kind of a thing. It can't take in one and then give you back another. In the way that if we have a promise of string and then we map over that and we get a promise event, we're probably okay with that. Like that seems like a reasonable thing to do. We do that all the time. But not in the case of a Redux store. So, all right. Any questions on any of that? It's subtle, but these are the things that kind of come up when you're thinking, would this work? So the cool thing about functors is it allows you to separate what to do from when to do it. Like all the logic about, hey, how do you know if it's okay to do things on the list? How do you know if it's okay to do things on the promise? How do you know if it's okay to do things on the channel or the stream or the whatever? That's the responsibility of whoever's writing the map function for that type. And that's done once and then never again, right? That logic is set up. And then as an outside consumer of that, all you do is you say what you want to do. And it figures out if it's okay to do that. So this sort of gets rid of all your checks to say, did I actually get something back? Like you don't worry about that. If it's a functor, because you can just, like a maybe, as an example, because you just do your thing, and if it's got a value, it'll be performed, and if it doesn't, no problem. You just move on. So as a sort of trivial example of this, we have some operation that might fail, and normally it's on us to check that. Did it get a value back? If it did, do this thing, otherwise do this other thing. If what instead came back was a functor, then we could just map something over it, like use our magical map that works for this particular functor, map this operation on it, and then run it through this from maybe, which extracts the value back out. Like that takes our f of a and gives us just an a. Right? It extracts something out of the structure. And so, they both check for no value. They both handle that case. They both do an operation if it's okay to do, and they both provide a default if we didn't have a value. Right? So we're doing the same work, but it's structured differently. We're not doing conditionals. We're sort of like, do this operation, do this operation, do this operation. The conditional is hidden away inside here. Right? Internally, map for whatever our type is, our maybe type, has to say, well, if it's the just case, do this, otherwise, hand back nothing. And we could do something more complex. Let's say we do some AJAX request and we get back some JSON. We could, check to see if we have the JSON, and then do some operation with it, and then do some operation with it, and then, kind of whatever we need to do with our JSON. Alternatively, if the value that came back was a functor, if this JSON result is a functor, then we could simply map over it. Map. And at the end, what the from maybe does is it says, if it was a nothing, this is what I want you to use. If it was just, then give me the value out of the just. So it unwraps the value, but safely. So here we can just pipe. You can use ram to pipe to just run, do these things. I don't care if we had a real one or not. If we actually were successful, just do it as if we had been successful. And if it wasn't, the maybe type in this case would take care of that for us. And we're using maybe here. There are lots of different functors. Like we saw that list, promise, and maybe all had different kind of semantics around what map meant to them. And we can make up our own types, and we can ascribe any semantics we want to what mapping over it means. Oh yeah, so they all have they both have default. They both have things to do. And I guess I didn't put the decision, right? The decision for what to do, if we should do it. Okay, so the map for each functor gets to decide the rules. And that's pretty cool. So now we can take any function a to b. Like, we've got a lot of functions that are like thing to thing. There's a lot of those lying around. We can use any of those with any functor where the types match up, right? So any f of a, this function is compatible with. And it will produce an f of b, whatever the f was in that context. And that allows us to take a lot of things that were sort of standalone and reuse them in a new context. I guess I would go back to this real quick. So had this been a little bit different, had we been allowed to change our state, this is an example of like where partial application is very useful, is we have, let's say, this is an a to a function. So there's no problem using an a to a function in map. That's totally fine. It's just that if you are a functor, you have to at least allow an a to b kind of operation. It's not that you require it, it's that you must allow it. And in this case, we wouldn't want to allow it. But let's say we didn't have that problem. We have some slightly different version of Redux where this is an okay thing. Then we could totally use reduce. We could map over the store with reduce as the function. Except that this wouldn't quite match the structure, right? This is a something and an a to a b. So we could partially apply the message, and now we have our a to b function that we could pass into the map. So this is why if you look at the type signatures, almost always, the thing being operated on is the last thing. Especially if you return a new value, you'll almost always have those right next to each other in the signature. So you can do things like this. Partially apply that, and then use that as your mapping function. Okay, and then, so we can reuse a lot of functions now that previously we couldn't. And anytime we start to think about something that has structure or context or anything like that, we can start to think of it like, could I make this a functor? In the case of the Redux store, we realized we can't, but in many other cases we can. And if you can make it a functor, then you kind of don't have to think about it anymore, especially in type systems that allow you to express like a constraint on it. It means it will automatically be usable with any of those functions that are written in terms of functor, and just communicating to someone, hey, this thing's a functor, they automatically know what's going on. They know the way they can use it. So being kind of as not a design pattern, but a design tool kind of thing for guiding how you think about it. Functor is a nice, like we have monoid, we talked about that last time, right? Monoids are this conceptual thing that feels kind of monoidal or semigroup-ish, the way we're appending things and squishing them together. Functor is its own like unique space of conceptual stuff. Okay, so we talked about those higher kind of types before. A cool thing that we can do now is we can start to express functionality completely generically. Like this works for any functor ever. Like new functors you haven't written, any functor that exists. And some of these are fairly trivial because when you're talking about, some unknown functor of some unknown type, the number of things you can do gets small, right? But we can still do useful things. So for example, you could have a functor filled with values of type B, and you could use this replace function, which is a real function, and you get back a functor filled with the same number of values of type A. So it's like going to replace all the values in that thing with this other value. We can zip, so we can take a functor of type A and a functor of type B and give back a functor of type tuple of A and B, like a pair. And we can do that safely. We don't need to know what A and B are to do that operation. And we don't even need to know what F is to do that operation. We can do that in terms of, so these could be promises, these could be maybes, these could be channels, streams, whatever. We can combine them. Okay, the last little bit on functor is, we've been talking about this map operation that it has. Just like last time with the monoid and semigroup, it does have these two little laws. They're not complex at all. And its laws are, if you have the identity function, so the identity function is just, give me a value, I'm going to give you that value back. Right? Anything, a function, object, whatever. So the identity of 5 is 5. Or identity applied to 5 is 5. So if we map identity over a list, so the identity function comes in to list, The list says, okay, apply identity to every value inside here. Let's say there's just 1. There's just the number 5. We get back 5. Right? So nothing has changed here. And so mapping identity is the same thing as just identity. Like if you said identity applied to this whole list, you would just get back to the list. Right? It's the same thing. That's the first law, is mapping identity does nothing. And law number 2 says composition order doesn't matter. This isn't like associativity. It means that, I think it's easiest in code. So if you map a composed function, so increment then double, right? We're using pipe. That produces a new function that does both of those things. If we map that composed function over numbers, it's the same thing as mapping increment and then mapping double over numbers in order. So you can map a composed function, or you can compose maps altogether, and those are exactly the same. Now, these certainly may not have the same runtime performance. Right? This is a different signature. This means compose. That means do F and then do G, if that makes sense. This is like G parens F of X. It's like that kind of notation. So you can map them individually and compose that, or you can compose them first and map. So this means we can like move things around. In the earlier example here, we were piping individual map operations through, but it would be safe to instead map the pipe, the composition result of this, 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 and this. That would actually totally be safe as well. So we can move those around back and forth. All right, and that's it. Functors. There's not a lot to them. Map. 2 laws. But you can actually do a lot. Monoids and functors are actually like very common, very fundamental structures in category theory and in a lot of functional programming. You tend to use them a lot, and you tend to favor things being functors over being more complex, fancy things like applicatives or monads or things like that, because they're so simple to reason about. So people do definitely have a tendency to push the data structures to see if they can get them to do everything they need to do purely in terms of a map operation, which a lot can get done in that way. So if you're familiar with lenses, we've used things kind of like lenses in our code base. Like we kind of started with like the Ramda lens and then kind of made our own, and then we made new functions. They're not called lens anymore, but they're sort of derived from that concept. I didn't put the type signature in here because it's a little more complex, but to be a lens, like a lensable thing, a thing where lenses can be applied to your data structure, you only need to be a functor. So if you are a functor, then lenses can be used on your data structure. All those existing lenses and all the existing machinery around them. There's other derivations where you don't even have to be a functor, but that's sort of an easy starting point for that. So if you think of that just in sort of, by being a functor, now you can do these like nested traversal and update operations on my data structure, and I didn't build any of that. I didn't make that happen. It's just by virtue of being a functor, that works with me. Like I'm part of this ecosystem. You can actually do a lot more with this than you would normally think. And then it was asked about resources for sort of more broad category theory. Certainly this covers monoids and functors and stuff, but it covers more things. So Bartosz Milewski has a YouTube series, Category Theory for Programmers, and then also a whole bunch of blog articles. These came first, and then these came after. This is him teaching a class. So if you like someone standing up and talking and interacting with people, this is where you should go. And if you want more of a blog post that you can skim through and jump back and forth, this is probably the better resource. And that's it. You now know everything about functors.